This video introduces you to some other topics when talking about the physics of sound. So the first topic, it's something that's pretty well known probably to you, but sound waves can reflect off of hard surfaces, and also sound waves get absorbed into softer surfaces. If you've ever been in a recording studio or maybe seen a movie of some situation where musicians are working within a recording studio, they use these soft-sided walls to avoid echoes because all of their sensitive recording equipment, they don't want to record any echoes. They just want to record the sounds coming from the instruments the first time, not after reflecting. They don't want any echoes. So, but sound waves can reflect. And a drawing that sort of describes this, let me show you this. So let's say that this is a wall, and over on this side is some air. And here come some sound waves that come from some sort of oscillator, and their direction of travel is towards the wall like this. And so what I've drawn is what's called a ray, and each of these lines are individual high pressure peaks, and then the dark spaces in between are the rarefactions. Those are the low density locations. So I'll erase that. But yeah, this is an incoming sound wave, and what it does is it goes and it bounces off the wall like this. But if you look at how the waves do this, it's interesting. This wave only has partially hit the wall there. Let me actually erase the outbound part. Whoops. So, but this part of the wave has bounced like that, and so it kind of gets drawn like this. Can you see what's happening? It looks like there is an emerging wave like that. I wonder if you can see how I drew this as to how the reflection happens. So this is what an echo is. Like sound waves can reflect off of a hard surface. They can reflect off of even like the surface of liquids. And also sound waves can actually reflect off of other gases. Like if you have a very high density gas that sort of sinks to the bottom of, say, a well or something, or a hole in the ground, and you can have a sound wave that travels down and reflects off of the top surface of that high density gas, and also sound can continue into the gas. You can actually have a reflection from one surface as well as sound actually just keeping on going into that higher density gas. So like a partial reflection, a partial transmission. Okay, so this is, so I just described what's known as reflection, but there is a confusingly similar word that is actually a different physical phenomenon called refraction. And this is not as well known by people. So an example of a refraction could be this situation. Let's say here is a road and it is very hot. And so the air just above the road is very warm, but the air further from the air further from the road is cold. And what's interesting is if you make a sound wave into this medium that's got different temperatures, it turns out that the speed of sound in warm air is faster than the speed of sound in colder air. So you might put some sound into this air, but what happens is the part of the wave that's in the warm air gets to travel faster than the part of the wave in the cold air. And what it looks like is your wave bends like this. It looks like the path of your sound wave bends. This is referred to as refraction. It's a bending of the path, right? It's not a reflection, although it kind of looks like a reflection, but this is called a refraction. Yeah, and it's because of differences in speed in the medium. The speed of sound is faster in warmer air than colder air, so faster, slower. I mean, it could be the difference between, say, 343 meters per second and 342 meters per second. You know, it's not much of a difference, but it's a big enough difference to bend the path of sound. Okay, so the next topic is the idea of resonance. And so here is, for example, a sound wave traveling. That is, it's a disturbance, right? An energetic disturbance, and let's say it's traveling towards the right. If the frequency of this sound wave matches, say, the frequency of some sort of like oscillator, like for example, as an example, a wine glass, right, which is kind of like a bell, right? So if this wine glass has its own frequency of oscillation, right, that this frequency you could hear if you took a little hammer and you rang the wine glass without shattering it, right? So you could hear this frequency. And then what you do is you tune a speaker to play that frequency. This energetic, no, that's not how you spell energy. This traveling wave, this traveling disturbance brings energy on a wave with this frequency if the frequency of the sound wave matches the frequency of the way this glass would ring if you rang it, then the glass can absorb energy, right? And we say that the glass oscillates. It gains an oscillation energy. And if it absorbs too much energy, of course, it can shatter, right? And this is some opera singers have very strong control of their voice, and they can match their voice's frequency, the sound from their voice, to the sound that they hear a glass make if you ring it, like if you tap it and it rings. So they match it, and then it's a show of skill to maintain a tone and cause the wine glass to build up an oscillation energy, right? That's, you resonate the wine glass, and then if you continue to put energy into the wine glass so that the amplitude of the oscillations of the wine glass get too big, then the glass itself will shatter, right? You destroy the glass. Resonance is a very useful phenomenon, actually. And yeah. So another really interesting topic is called interference. And so interference is very cool. If you, let's say that you have a speaker and it is sending waves out from itself in this direction, right? And you have another speaker sending waves out from itself in this direction. If you look really carefully at the overlaps, this oops, right here is a place where you have high density from the blue wave as well as high density from the red wave. And that means that where I've circled is very, very high density. And here's another very high density, very high density. These are places that would push in on your eardrum very strongly, much stronger than just, for example, that place right there, right? That place might push in on your eardrum with a unit of 1, but this place up here would push in on your eardrum with a unit of 2 because it gets 1 from both waves. So that's called constructive because it's high density and high density added together gives you very high density. What's interesting is to look in this place as well. In that place, it's the low density of both the orange and the blue waves. So if, for example, right here is, say, -1 in density, and right here is -1 in density for the blue wave, then this place right here is -2, and it pulls out on your eardrum very strongly, right? So this direction is a place that experiences constructive interference. And if you place a listening device there, it would hear very, very loud sounds. But let me show you an alternative set of places that you can sit that are interestingly very different. Let me see. I kind of messed up my drawing here. So let me circle some spots. If you look at this place, and this place. So if you look at the first circle I drew, it's a place that's the orange wave's high density, but it's the blue wave's low density. So this is kind of like adding 1 from the orange wave and -1 from the blue wave, and it adds to 0. This is the place where the two waves destructively interfere, and this would be a place where you don't hear any sound. You would actually have the overlap of two sounds, but you would be in a location where the two sounds cancel each other, right? So this is what's sort of the basis of a noise canceling earphone. So noise cancellation is based on destructive interference. So you use basically a little computer to listen to the sounds coming from the outside, and that computer very quickly creates the opposite sound. In a sense, the sounds from the outside are coming in as ones, and the noise canceling headphone creates the -1 version of it. And you hear both of them overlapped. And so what shows up at your eardrum is quiet, which is very strange. You're adding two sounds together to get no sound. But you're doing it in a very, very particular timed way. Right, so that's called noise cancellation. Okay, so another topic is the idea of beats. So beats is what you get when you get the overlap of two sounds of different but similar frequency. So they're different, definitely, but they're almost the same. That's what's meant by similar. So for example, how about 250 and 252 hertz, right? Can you see that they're real similar? They're both very similar to 250, but they're not the same. They have a difference of 2 hertz, right? So they're still different. So what that looks like is the following thing. So let's draw a picture of the 250 hertz signal. So that's the lower frequency, right? 252 is bigger. So if it's lower frequency, it doesn't happen as often. So I'm going to spread out the waves because they don't happen as often. But the blue wave is the faster frequency. So it happens more often. So let me draw a blue wave. If it happens more often, can you see that they're going to be closer spaced together? And what's interesting about this is you can begin to see that sometimes the waves don't line up, but sometimes they do line up. So let me point out that here is a position that's going to be loud. But for example, this position is going to be quiet. And it's quiet because the blue wave has a high density peak at the orange wave's low density location. So that's a cancellation, right? That's a destructive interference. The loud place right here is where the orange and the blue at the same time, at the same place, have their high density peaks. So what's happening is you have this series that are more spread out of loud and quiet locations. So here's another quiet, and then this is loud, right? And then this is more quiet, and then this is loud. And so what your ear is going to hear, right? This is somebody's ear. So as these two waves, right, they're going to travel at the same speed. They have different frequencies, but they have the same speed of sound. And they go towards the ear. And the ear, right, this ear right here is about to hear this loud sound, followed by this quiet sound, followed by this loud sound, quiet, loud. And that is what is called beats. Yeah. What it sounds like is wow, 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 wow. That's what it sounds like. Okay. And that's it. So those are some basic physical things that happen with sound. This is going on all the time, all around you. Most of the time, there isn't any interesting information in the sound. You know, it's just noise and your brain is really good at ignoring it. But sometimes you can pick out really interesting features. Like you can pick out an echo, right? That's an interesting feature. Refraction might be hard to tell, but sometimes refraction, I think you'll notice it if you see a lightning strike, but you never hear it, right? That could be a case of different temperatures up in the stormy weather, and the sound coming from the lightning strike, it might be headed towards you, you know, in the direction of where you're standing for a little while, but because of where the warm and the cold atmosphere is, the sound might bend away from its direction towards you, and you never hear it, but you definitely see it, right? Yeah, resonance is a very interesting feature. Maybe you've seen footage or like allusions to opera singers breaking glasses with their voice. Interference is, you might have heard interference in sound art. Actually, sound art likes, people like to use beating as well. It's an interesting kind of like thing that feels a little dissonant. It sort of it gives you a sort of a funny feeling. But yeah, okay, so interesting stuff.